Okay, so obviously, effective field theory has been a very powerful framework and a very powerful tool to understand the dynamics of quantum field theories. However, the sort of purpose of this talk is to argue, or at least give some motivation for why considerations beyond our current knowledge of effective field theory, and perhaps especially considerations to do with gravity, may be essential to the resolution of some of the practical long-standing puzzles that we've had in particle physics. In many ways, in ways that will guide model building and the specific extensions of the standard model that we consider, and in some cases, even in ways that we can pursue experimentally. So obviously, understanding the consistency conditions on effective field theories that effective field theories need to satisfy in order to be compatible with a gravitational UV completion is a work in progress. What I'm going to discuss here in the interest of time is only a couple of ideas that I find interesting and sort of that represent this general idea. I should say that what I'm going to discuss here will appear in a more comprehensive manner in this upcoming white paper with my collaborators, Patrick Draper and Matt Rees. And I promise that that will be a lot more comprehensive and a lot more references will be included. I apologize in advance for not being as comprehensive as I should be in this talk. So the expectation that not all consistent effective field theories will remain consistent when they are coupled to gravity is not only reasonable, but it's also true. And the earliest example of that was the requirement that any consistent theory cannot have gravitational anomalies. Other consistency conditions on effective field theories are mostly in conjectural form. So in previous talks, we've already heard about the requirement that there cannot be any global symmetries. A closely related idea that we'll discuss more later is the weak gravity conjecture and other related ideas like the completeness hypothesis or the distance conjecture and so on and so forth. So this allows us, in principle, to try to differentiate or categorize all the group of effective field theories into the landscape of theories that can descend from a consistent theory of quantum gravity, such as a string theory, versus the swampland of effective field theories that are not compatible with a gravitational UV completion. And of course, the hope is that that would provide a powerful discriminating tool as applied to low energy effective field theories. So let us discuss, first of all, I'm going to discuss focus on symmetries first. Obviously, the concept of symmetry in the context of effective field theory has been a very powerful tool to understand in our understanding of particle physics. A very important concept that has guided the way we think about many of the questions of the standard model is the concept of naturalness introduced by Hooft. So the observation that quantum corrections respect the symmetry of a theory suggests that it is not unnatural to wander around a symmetry-enhanced point in theory space. This notion of naturalness has been a major guiding principle in model building and in motivating the extensions of the standard model that we consider, but it is also clear that it is very much in tension and perhaps in some extreme sense, even inconsistent with these expectations that we cannot have global symmetries in a theory of quantum gravity. So that as we move in theory space towards a point where a global symmetry is restored, what becomes clear is that what we're actually doing is we're traveling outside the landscape of effective field theories that we know will be compatible with gravitational UV completion. So it is clear that we need a more sophisticated version of Hooft naturalness. A more sophisticated version is necessary in the presence of gravity. That more sophisticated understanding obviously needs to preserve the existing successes of this framework. but also must resolve this tension, the current tension with quantum gravity. And of course, the hope is that that improved understanding of symmetries might give us some new insight or perhaps some new guidance on some of the problems of the standard model. So from this point of view, again, theories that have an almost global symmetry are not so much technically natural as, we would say perhaps highly suspect. Obviously, in order to make significant progress in this direction, we would also like to have a quantitative understanding of how global symmetry violation occurs in theories of gravity. There are a number of issues, a number of open questions that, I'm just going to bring up as questions that we would like to answer in a systematic way. So exactly, what form takes global symmetry violation in theories of gravity? Are all possible symmetry violating operators generated? What is the size of these effects? Are some of them larger than others? Perhaps it is a certain class of higher dimensional operators that are generated with a certain dimension. So perhaps there are some type of selection rules. In more general UV completion, such as string theory, how does the size of that global symmetry violating effects depend on the underlying parameters? If we buy the picture that there is a landscape of vacua, such as we believe might be the case in a string theory, is it possible to tune that global symmetry violation almost to zero? How much is it possible to do this in a theory that has a discrete number of vacua as opposed to being a continuous landscape? Obviously, I don't know the answers to these questions, but these are questions that we would like to make progress towards to understand this problem. What about zero versus finite temperature? The rate of global symmetry violation by gravity in particular doesn't have to be the same now as it was in the early universe. The standard model is already an example of this. Is there a universal origin for the violation of global symmetry? So early back in the days, when people started thinking about this, wormhole calculus was one of the first ways people tried to estimate how gravity violates global symmetries. In more recent times, people have tried to come back to this question, and actually now, after the recent progress in understanding the black hole information puzzle with the role that wormholes play, people are trying to come back to this question of what is the effects of these geometries on violation of global symmetries. It is possible that, and a variety of bottom-up arguments and calculations, including gravitational instantons, suggest that perhaps there is a universal lower bound on the size of global symmetry violation in gravity that looks something like this. So it depends exponentially on the Planck scale and the cutoff scale of the theory. But that doesn't have to be the end of the story. Different ways of realizing an almost approximate global symmetry may meet different constraints. And this is not only a question that is theoretically important, it also is important in practice. It could lead to proton decay aside from, grand unified theories. Baryon number violation in the early universe. So generating a baryon asymmetry we know requires baryon number violation beyond anything that happens in the standard model. Again, understanding how baryon number is violated by gravity in the early universe could give us some insight into how that baryon asymmetry was generated. Similarly, there are a number of parameters in the standard model that are small enough so that we are, certain symmetries are close to being approximate global symmetries, as it is the case with neutrino masses, and potentially also lepton number if those neutrino masses are Majorana masses. So what are the implications of global symmetry violation in gravity for these types of observables? And similarly, for the Yucava planes of the light standard model fermions, and so on and so forth. There is one context in which the importance of global symmetry violation has been long recognized, and that is in the context of solutions to the strong CP problem based on the QCD axiom. So in particular, the fact that it is necessary to introduce an almost exact U1 global symmetry, the U1 Petzia-Queen symmetry, in order to solve the strong CP problem in that context. So this also goes by the name of the axion quality problem. So one could try to solve the axion quality problem and introduce additional structure that makes that symmetry an accidental, almost exact global symmetry that typically changes the phenomenology compared to the vanilla QCD axion. So this is an example in which these kinds of considerations can highlight phenomenological differences between and in this case, the standard QCD axion versus the way in which we try to understand why a certain symmetry is very close to being exact. We could also try to take this mandate more literally and just look for alternative solutions to the strong CP problem that do not require introducing any kind of approximate global symmetry. One example of this are solutions to a strong CP based on restoring parity. And in this case, the phenomenology of this class of solutions is very different from the QCD axion. Not only that, the breaking of parity that we expect by gravitational effects can highlight additional opportunities to explore these models, both at EDM experiments and also via gravitational wave observations. Beyond gravity, we heard a beautiful talk on Wednesday by Shuhen Shao, who told us about all the developments in our understanding of symmetries that have taken place in formal theory over the last few years. So far, of all of these categories, really the only class of symmetries that we've used to understand particle physics, and that we use to understand, how to solve those problems and go beyond the standard model are basically ordinary symmetries. So it's completely clear that we're using a very small fraction of all the possible set of tools in quantum field theory to understand the features of the standard model. And that fraction is clearly becoming increasingly small. Okay, I have 3 minutes. One avatar of the statement that there can be no global symmetries that is particularly interesting, and that also goes a little bit in the direction of making that statement a little bit more quantitative, is the weak gravity conjecture. As you've heard many times, this is sometimes summarized through the slogan that gravity is the weakest force. And in some sense, I think is more natural to regard this as the gauge theory version that there can be no global symmetries in a theory of quantum gravity. So in a theory with a U1 gauge factor coupled to gravity, the weak gravity conjecture basically translates into the requirement that there must be a super extremal particle whose mass is bounded by the product of its electric charge times the Planck scale. And similarly, a similar argument as applied to magnetic monopoles results in an upper bound on the cutoff of this theory as G times M Planck. So this basically restricts us from getting too close to being able to recover a global symmetry by lowering the cutoff scale of our theory as we try to get too close to that swampland of theories with exact global symmetries. As it is very nicely discussed in this very extensive recent review of the weak gravity conjecture, the fact that it is a conjecture means that we don't know exactly what this conjecture means. So there are a variety of versions of what this means, also versions applying to axions as well as generalized higher form symmetries and not completely unrelated discrete symmetries. In the case of axions, this typically translates into an upper bound on the action of instantons charged under the shift symmetry of that axion. In the context of higher form symmetries, this can imply an upper bound on the tension of a string, for example, or other extended objects that typically makes these objects be self-Planckian. Okay. But the various avatars of the weak gravity conjecture can have important implications for particle physics. So something that has been explored for a long time is the implications for axion inflation. In particular, it makes it very hard to realize axion inflation in a way that the field range of that axion is parametrically self-Planckian. Also implications for properties of axions, as has been discussed by a number of authors, including the QCD axion, but also beyond. The weak gravity conjecture, as an upper bound on a mass scale really begs to be used as a tool to address the electroweak hierarchy problem. And I myself have thought about this. Implementing this idea in practice is non-trivial, and in some regions of parameter space, it can have implications both for Higgs properties and also properties of dark matter that we can, at least in some region of parameter space, probe experimentally. And then some other more conjectural versions of the conjecture can also be applied to the understanding of small neutrino masses, and possibly also connecting that to the weak gravity conjecture. Okay, so in my last minute, I'm just going to throw something out there, which of course, if I'm going to be speculative, let me just finish talking about the cosmological constant problem. So a very surprising aspect of gravity that has been understood in the last few decades is the fact that the entropy of gravitational system seems to be a subextensive quantity. This is obviously very different from what we're used to in the context of local quantum field theory, where we learned that entropy always scales like the volume of a system. So this clearly suggests that local quantum field theory overcounts the number of degrees of freedom in a gravitational system. And it was beautifully articulated by Cohen, Kaplan, and Nelson that this could have profound implications for our understanding of the cosmological constant problem, or at the very least, the way we formulate that problem. So very basic observation is that a very reasonable order one requirement for us to use effective field theory to describe a system of finite size is that that system itself is not a black hole, okay? So in the context of quantum field theory, if I have a system with size L, so volume is L cubed and energy density is lambda to the fourth, requiring that its size is above its Schwarzschild radius gives me an upper bound on the UV cutoff scale of the effective field theory that I can use to describe that finite size system, okay? So this suggests some kind of connection between UV and IR. Notice in particular that if I chose the size of the system to be the de Sitter radius of expanding universe, this cutoff scale would precisely correspond to the energy scale. This would be like raw vacuum to the 1/4, the energy scale corresponding to the vacuum energy density. So this very much suggests that vacuum energy is only sensitive to the UV up to scales that are on the order of Roof and Planck on the de Sitter radius. How this is implemented in practice is an open question, but there has been some recent interesting ideas by these two authors suggesting that a possibility is that what is taking place is a depletion on the number of degrees of freedom at energies for a system of finite size at energies above this combination. So again, in the context of local quantum field theory, at energies below this scale, the number of degrees of freedom in a momentum space volume would scale in the usual manner and would be proportional to the volume of the system. But above energies given by this combination, then the number of degrees of freedom gets depleted in a way that looks like the system is basically takes a finite size where this bound is saturated, okay? This very much suggests, and certainly the considerations discussed by these three authors already suggest that when we discuss the cosmological constant, we probably shouldn't be talking about, sensitivity of the vacuum energy density to scales to UV scales, to heavy degrees of freedom, or corrections to the raw vacuum from higher dynamics. That a three-level explanation of why this ratio is tiny should be enough to solve this problem. So this is very much sort of, many of us probably have heard Tom Banks express, intuition like this in the past. I feel like there has been progress along these lines in recent times that actually try to make that a little bit more precise. There's been also a lot of work, and I'm just about to finish on trying to understand what all of these consistency conditions like no global symmetries with gravity conjecture come from the bottom up. This was initiated by Nima, Sergey, and collaborators, and then a lot of people here, including Grant Remen and collaborators, have pursued this program with increasing success. And there's obviously a lot more interest now after, as I said, the recent semi-classical gravity progress on the black hole information puzzle. So this is my last slide. A lot of opinions and feelings are expressed often about how we should interpret the current absence of experimental guidance, in particle physics. I think what it is not an excuse to stop thinking about the long-standing puzzles that we have in particle physics, but I do think it is a mandate to try to think about those problems differently. Probably not all the problems of the standard model will require new developments in quantum field theory or considerations related to gravity to be resolved, but it is conceivable that some of them do. And I think it is our job to explore that possibility. And that means developing concrete examples that address the puzzles that we have in the standard model, and then exploring what the experimental implications of those are, if any, okay? I think at this time, there are still many major conceptual puzzles that we don't understand. It is also clear, and we had many great talks over the last couple of days summarizing a lot of the progress on the formal theory side that's been happening over the last few years. And at the same time, we live at a time where there are more experiments probing physics beyond the standard model than ever before. So to me, this seems like it's a very exciting time to be thinking about some of these questions. So thank you, and thank you especially to the organizers for organizing this really nice conference.
Any very quick questions? Online? Well, thank you very much.
Thanks.